So welcome to linear algebra class. And what I want to do today is work out quite a few problems using Matlab and talk about the theory. So today's class, we are going to go back and forth between Matlab and linear algebra Blackboard class. So please, first and foremost, I want you to go to Canvas. Can you see my Canvas module? So I want you to go to Canvas. Please go to modules and then download lecture 7 code.rar. So please download this zip file. And please unzip it. It contains the data that we need and the codes that we need for today's class. So were you able to download the file? It may take some time, but you should download the file and unzip it. Okay, so assuming you got that, so let me outline what we are going to do today. In the last class, we talked about few important concepts. We talked about something called as the tensor decomposition. We also talked about something called as the randomized linear algebra, which is also called as the randomized SVD. And we talked about the theoretical basis for performing these processes or these mathematical operations. So what I want to do today is, first and foremost, I want to explain to you a very, very interesting example. And this is sort of a famous example, which is called as the Eigenfaces. So what the Eigenfaces? So what that example does, so basically what we have is we perform PCA. So we perform principal comp. Could you say it again, please? So we are going to. Could you try again? Is anyone's Siri on?
Yes, Siri is
on. So we are going to perform PCA. And we are going to perform PCA by using SVD on mean subtracted data. So what we are going to do is we will have mean subtracted data, and we are going to perform SVD on this mean subtracted data, and we are going to find out the most dominant correlation. This is important. Most dominant correlation. And try to find out a new coordinate system, and we will try to use this coordinate system and try to classify the images. And for this we are going to use something called as Eigen Phase database that comprises of lots and lots of images. So Eigen dataset. And what we are going to do is we are going to use 36 people from this data set. So we are going to use 36 people from the data set. And what we are going to do is we are going to hold two images back from this data set. And then what we would do is we will try to map those images. And then once we map those images, we will try to find out the important common features. We will try to find out the most important and common features from this data set. And you would realize that once we perform this decomposition, what we can do is those features that the PCA identifies, they can be used not only for classification, but to find out the correlation. And basically those eigenfaces are sort of the principal component, or think about it like eigenvectors, that would allow us to reconstruct the images. And when we use those features to classify the images that we held back, you would realize that we are able to perform the classification very, very accurately. So what I'm going to do is I'm going to take you to Matlab, and then we would work out the problem. I will explain the code and we will go line by line. So at this point, I'm going to share my Matlab screen. But before I share my Matlab screen, please make sure that you have all the data unzipped into your Matlab folder, and we can actually do some coding. So what I'm going to do is I'm going to share my Matlab screen. Okay, can you see my Matlab screen? So let me close everything, and I want you to follow what I'm doing. So first and foremost, once you open the folder, you should be able to see truncation, SVD not aligned, aligned, RSVD, RSVD.m, Jupyter, Eigenfaces, Eigenfaces2, CT tensor, and allfaces.mat. So these are the files that you should have inside your folder. The first example that we are going to learn start is nothing but Eigenfaces _ex. So double click on this, and now you will see this Eigenfaces example. So what this code is doing, I'm going to go line by line. Line number 1, we are clearing everything, closing everything. Line number 2, nothing. Line number 3, we are loading that face data set. So allfaces.mat is nothing but the matrix form of YEL data set that I just talked about. So all those matrices are stacked in allfaces.mat. And what we are trying to do is we are trying to load that huge data set. Then what I'm going to do is I'm going to create sort of a matrix with zeros. I'm going to create the matrix with zeros. And the reason for that is I want to fit all the data. And then I'm going to have my count as 1. And then I'm going to run a loop I and j, wherein I'm going to read all that data and reshape it and try to load those images. So what I want you to do is I want you to highlight and follow my lead, highlight the first section, just highlight the first section, and either you can run section or just say evaluate selection. And then you should be able to see all the faces. One figure will pop up, and these are the images. Are you able to get those images? Everyone got those images? So basically, these are different people in that Yale data set. So these are all the different people in the Yale data set. Now, what I want you to do is, I want you to run the second part of this code. So highlight the second part of the code. Please highlight the second part of the code and run. Can you see the second part? Can you see that now you have the image of just one person, but under different lighting conditions and slightly different angles? Are you with me so far? So any questions here? This is the Yale data set that we are going to deal with. So the first part of the code gives you the images for all people, all persons, but please note it's a grayscale image. And the second part of the code is going to get image of just one person. Now, what we are going to do is we are going to process this data. So I want you to run the code Eigenfaces 2.m. You got the same image for both parts. Did you close the first image? Or what you want to do is, Borna, if you are here, let me show you something. Just add this line and then it will make sense. Figure. Can you see add line in line 34, just add figure. And in line 15, take out, yeah, you can say figure 1, that's fine, figure 1. And now if you run the code, you are going to get tons and tons of images. Are you with me so far, Borna? Okay. All right. Now you have to close all those images. So that is how that Yale data set is set up. So first section of the code will give you different faces. The last section of the code will give you same face, multiple images. Okay, now we are going to look at the Eigenfaces 2 example. Are you with me so far? So in this example, again, what we are going to do is, for line number 1, we are going to clear all, close all, and then again load all faces.mat data set. And here is what we are going to do. We are going to first load 36 people from the training data. So please understand that we have 36 people from the training data. We are going to use them to train and to find out the most common features. So please note, this is the training faces data. I'm going to find out the average and subtract the average. This means subtraction is done so that I can find the SVD, and that's going to give me PCA. Remember, PCA is mean subtracted SVD. And then I'm going to find out the SVD. So X is the matrix, and this matrix is nothing but the training data set minus the average that's subtracted. And then what I want you to do is, for a second, just highlight this code and click here and say evaluate. And once you do the evaluation, you are gonna get one eigenphase. So you are going to get just one eigenphase. And it may take some time because it's a huge SVD that needs to be performed. There are a lot of operations that are happening. So can you see, you should be plotting two images, figure 1 and figure 2. Do you agree with me? Did you get two figures? So what are these two figures? These two figures are the first and second principal component from that data set. Are you with me so far? This is the first and the second principal component of the data set. If you really want to go further, then you are welcome to change this to maybe 3. And then you can actually perform. It will take some time. So it's going to give you the most dominant features from that training data set. It will take some time, but bear with me. So again, you will see the first and the third, the eigen image or eigen face. Are you with me so far? You can keep on changing this, and then you will see if you change this to first, this will give you the first eigen face. If you change this to second, it will give you the second eigen face. If you change it to third, it will give you third eigen face. Everyone understood this? Is your code working? Okay. Now here comes, yeah, Trenton, you can ask, do you want, I can actually unmute you, or you can ask me, yeah, you are unmuted, Trenton.
Can you hear me?
Yeah.
Okay, so just out of curiosity, in the data set that I think you gave us file-wise for lecture 7 code, it says that the training faces are equal to faces to the row, to all the rows, comma, to the sum of all the columns is what I see, and not minus. So I was just wondering what's up with that.
So line number 10, are you asking me a question about the line number 10 that I highlighted
no, 6
here?
and 7. 6 and 7.
Line 6 and 7. Okay.
Yeah, they're saying on the code it says equal
Conditioning.
to and not minus.
Sorry, I missed the last part. What is it?
It on the code it shows equal signs rather than subtraction. That's all I was trying to figure out what was going on with that.
Here? Here?
No, line number 7.
Can you tell me? Line number 7. Oh, yeah. So average face is equal to mean training faces by 2. Is this what you're saying?
Oh, sorry, hold on. My display was messed up. My bad. I thought I was subtracting to it, not equaling to it on your side.
Okay, it is taking time. Okay, I will show you the results. Just a second. Okay, does that answer your question, Trenton? Okay, so I'm going to lower your hand. Okay, I'm going to lower your hand. Okay, good. So, all right, I'm going to show you the results. Just bear with me. So I'm going to show you the first eigenface. Actually, you should definitely do it because this is more fun when you do it in person. Because you will, so just a second, I'm running the code. Okay, now I'm gonna share my screen. So it's a different screen that I have to share. So bear with me for a second. So Can you see the first eigenmode? Viraj and Diksha. Okay, now I will show you the second eigenmode. Disha, okay, yeah. So this is what you should be seeing. And please play with that and you will see that all the eigenfaces. Okay, I'll go back to Matlab. So is it mapping the common pixels? So what it is trying to do is it is taking that huge data set, and this is answer Bodna's question, and trying to find out the most predominant features. Now this is actually more interesting. The next part is more interesting. So what I want to do is, we are going to actually start playing with the images that we did not use earlier. So we are trying to do the reconstruction, and we are going to find out how that reconstruction works. So we are going to find out how that reconstruction works. So what we are going to do is highlight the second section of the code. So please highlight the second section of the code and then run. And what I want to tell you here is that I'm going to have different eigenvectors. So for example, I would have so here R stands for the number of eigenvectors or eigenfaces. So I can start with something like this. So start with 25, okay? Start with 25 and just run this code. Start with 25 and run this code. And you will see that you are going to get an image, and that image will be good, but not great. Then what I want you to do is, I want you to do it with 50. I want you to do it with 100. I want you to do it with 200. And then you will realize that as you start including more and more eigenfaces, your reconstruction is going to be much, much better. So please try that. And then you will see that your reconstruction is going to be much, much better. Now, the next thing, what I want to do is, this is very important. So I am going to use the eigenfaces as the coordinate system. So reconstruction means that initially you had that huge data set. You decompose that in terms of its features. So as you can see, if you include more eigenfaces, as you include more and more features in your data, the reconstruction becomes better. So let me show you just a second here. So last part is, I want to do this, and this is the important part. So if you were to evaluate the last section, what is this doing? This is the projection of images from the two images. That images, they belong to person 2 and person 7. So you will see the red triangles and black rectangles. So what those are all the images from two individuals onto 5th and 6th PCA modes. And what does that mean is, it kind of tells you that where those two people are in terms of their images. And what this kind of tells me is, this is giving me a nice classification. It's giving me a nice boundary. I'm getting a nice boundary between these two. Okay, so what I'm going to do here, real quick, I'm going to add a figure. And I'm going to construct Now, are you able to see that? Okay. So what I want you to do is, did you add did you add figure in line number 25? And then highlight the whole thing and run. So I will show you what I'm seeing. Hopefully that will make sense. So this is what you should be seeing. Are you able to see this? And the last part that you should be seeing is this figure. Can you see this figure? So this blue dot is telling me, this blue dot is telling me that where that person is. So these images can be mapped onto the eigenfaces. So the red and black dots, oh, you will have to run the whole thing. So you will have to run the whole thing, and I will try to run this whole thing. And then you should be able to see those red and blue dots. So the key idea is we are trying to project these two people onto the modes, and that allows us to see where those people lie, and then how is their face similar to other faces. Now, next thing what I want to talk about, and this is an interesting example, is I want to look at this truncation.m. So please open truncation.m. And this truncation.m example is sort of a toy problem, but this kind of explains the truncation alignment, importance of truncation alignment in SVD. So in this problem, we are going to construct a matrix and then try to add some Gaussian noise to this matrix. So as you can see, we are going to create a matrix, and then we are going to add a noise to it. And then what we are going to do is we are going to see if we can somehow use SVD, for filtering out the data. So if you can use filtering to filter out the data. And what we are going to do is we are going to do this with something like a hard threshold, and then we are going to add some sort of cutoff. And how would we do this hard threshold and cutoff? It's again dependent on the number of singular values that we are going to retain. So basically, this is where we talked about. This is the entropy. And what we are going to do is we are going to find out the 90% of the entropy or 90% of the energy. So I want you to run this code, and then you will see that you are going to get some interesting images. So you should be seeing 6 images. Do you have 6 images in front of you when you run this code? Once you run this code, you are going to have 6 images. Figure number 1 is nothing but the original image. Figure number 1 is the original image. Figure number 2 is the noisy image. And figure number 3 is the threshold image. And then what I want you to do is, I want you to look at figure number 5 and figure number 6. Figure number 5 talks about actually shows the decay of the singular values and its cumulative energy. In other words, entropy, the information that is retained. So you would see that in figure 5, you are going to see the cumulative energy actually the singular values. So you can see the singular values. First singular value is 154. Then you see second singular value is 129. Then you will see that all other singular values, the third singular value is 49. Then gradually, if you move around that plot, then you will see the singular values become less and less and less and less. Are you with me so far? Did you able to get the code running? So, okay, so figure number 5 is the decay of the singular values. So what this particular thing is telling me that the first 2 singular values are the super important singular values, and afterwards the singular values, they start dropping down, and that actually helps me filtering out the data, and that's what exactly is happening. So if you were to look at the original image in figure 1, even if I corrupt that with noise, this is a very important observation. I want you to look at figure number 1. Figure number 1 is the original constructed data. That is the clean data. But in life, we are never going to have a clean data. So the data will be figure 2, which is the corrupted data. But what I'm doing is I'm using singular value decomposition to denoise the data. Are you with me so far? And I would repeat this once again. So please open figure number 1. Figure number 1 is the actual data. And you can see that data is crisp. Figure number 2 is the data that is corrupted by noise. And believe me that even if you are doing an ultrasound, if you are doing maybe a CT scan, even if you are doing an MRI scan, the data that you are going to get is going to look like figure number 2. So the key question is, if we have figure number 2, how do we filter it? How do we parse that figure so that we get the best possible reconstruction? And the way we can do the reconstruction is by singular value decomposition. And in figure number 3, we have used singular value decomposition to denoise the data. Are you with me so far? This is exactly how the MRI imaging, CT scan imaging, and for that matter, ultrasound imaging works. So how is this denoising done? This denoising is done by means of singular values. As you can see, we retain the first few singular values, and we actually, so what this is telling me that the last singular values, the last bunch of singular values, they correspond to the noise in the data. So those can be ignored. But if I were to retain the first most important singular values, I can denoise the signal or denoise the picture. And believe it or not, in your iPhone or smartphone or iPad, you have something called a de-blurring. So if you have a picture that is blurred, and if you want to sharpen the picture, this is exactly what they do. For example, if you are using Photoshop and if you hit the like sharpen the image, this is how the image is sharpened. Are you with me so far? Yes, you can do the exact same thing on noise audio recording. Exactly. OpenCV is going to implement singular value decomposition to do this deburring or denoising. So OpenCV internally uses PCA, principal component analysis, to perform this. As a matter of fact, there is, if you go a step further, there is something called as upscaling. So if you have a 1080 video and you want to convert that into a 4K video, something similar is done. But only thing is what they do is they do interpolation in between those eigenfaces. Everyone understood this concept? Any question? This is very important. Yes. When you say GAN, it is generational adversarial networks, and you can basically some of these concepts can be used in GAN. Okay, any other questions? Okay. Next thing is I want to look at the next file, which is SVD aligned and not aligned. So here is the limitation of SVD. So if you have an image that is not aligned with the previous image, then your SVD is not going to be accurate. And that, unfortunately, that happens all the time. So if you have an image, so we need to align the data. And there are techniques for alignment. And if you are using OpenCV or some other software, you can actually take care of alignment in the software. But I want you to run this code, SVD not aligned. And I will actually go through this code a little bit. First, we are clearing everything. Then we are creating a matrix. Then we are creating a subplot. And then I'm rotating this cube. So I'm trying to create a cube. And I'm creating a cube externally dark dots, and at center it has white dots. So please run this code. And after you run this code, you will see one figure, and I will share my figure with you. So I want to share my figure with you. So this is what you will see. So what I have is I have a cube on the left hand side with 0 rotation. Everything is super aligned. And what I have is I have the cube that is inner rectangle or inner square that is rotated. So what happens because of that is you get additional singular values, additional non-zero singular values at the bottom because of this. I am rotate. I don't know. Okay, let me see. Do you have the exact same code? Let me copy and paste that code in the chat window. Oh yeah. So actually, yes, you're right. I'm rotate is a special function. You need to have the image processing toolbox. So you can go to Matlab, go to add-ons, go to Matlab, go to add-ons, and then there you can actually download the toolbox. So you will realize that you are going to have variation in the singular values because those two images are not aligned. So alignment is very important in the case of singular value decomposition. Now, next thing which I want to talk about is actually, it's very important, is something called as the randomized linear algebra. And I want you to open this code, which is called RSVD. So now what is this RSVD code doing? In the last class, I talked about randomized linear algebra. So what is the purpose of the randomized linear algebra? So here is the idea. So you have this huge matrix. You are going to use the sampling theorem and then get the basis vectors and then use that basis vector to find out the column space, and then you will find out the rank. So I'm going to type the technique here, or I'm just going to tell you what that is. First, you want to find out a particular rank, and this rank is less than the actual rank. Then you are going to use something called as random projection. You are going to use random projection to sample the column space. So what I want you to do is, step number 1 is choose an appropriate rank. And this choice of R is arbitrary, okay? Then what you're going to do is, in step 2, you are going to use random projection to sample the column space. And that is exactly what is happening from line number 3 to line number 5. So that exactly is happening from line number 3 to line number 5. So, and then what we are going to do is, we are going to construct something called as the approximate column space. So next part is construction of approximate column space. And how is this approximate column space constructed? It is nothing but Q multiplied by Q transpose multiplied by X. So using the random projection P, I'm going to call this random projection P, and we sample the column space and we find matrix Q. So we use a random projection, and when we call this random projection is nothing but random sampling. And then what we are going to do is, we are going to project X. We are going to project X into Q subspace. Project X onto Q subspace. Project X onto Q subspace, and then that leads to Y is equal to Q transpose X. And then the last part is, we are going to construct the U. This is the high dimensional mode, which is given by Q multiplied by U Y. And this algorithm may look convoluted, but believe you me that this entire randomization algorithm is implemented in 13 lines of code. So, and I'm gonna go basically line by line. Everyone, do you have RSVD, which is randomized svd.m file in front of you? I want you to open the randomized svd file. In the randomized svd file, the idea is we are going to do the random sampling. And when I say random sampling or random projection, means just picking up the numbers from the column randomly. So function line number 1, I'm defining a function RSVD. In step 1, I'm going to sample the column space. So first of all, I'm going to get the size of X, and then I'm going to construct this P. Please note this P, or this is called as the projection matrix. This is constructed using a random number. And then I'm constructing this Z, which is nothing but X, which is the initial matrix multiplied by P. And then I'm gonna construct this subspace in this for loop running K1 to Q. And I'm just for the sake of simplicity, I'm calling this Z. And that Z is X multiplied by X transpose Z. And please note what that X is. X is the initial data set. And then what I'm doing is I'm doing a QR decomposition. Wait. You can't run this code. Viraj, you can't run this code. This is a function. If you click on this, this will throw an error. That's totally fine because it's a function. You cannot run the function as is. You need to provide the arguments. Okay. And then in next step, we are computing the SVD on projected randomized basis. And then actually I'm doing the SVD, which is the economic SVD. And if you, I strongly recommend that run this code line by line when you have time. And then you will see that this is actually a very simple application. So what is the application of this RSVD? So for that, I want you to run RSVD run. Can you open RSVD run? Everyone, RSVD run is the application of randomized SVD. Can you see this code? Are you able to open this code? Okay, and now please run this code. And this code is going to perform SVD and it's going to perform randomized SVD. And you would see a very nice figure. And I'm going to share that figure with you in just a second. You should be able to see this figure. Are you with me so far? So what this figure is telling me is you have the high resolution image of the Jupiter on the left. Okay, you have the high resolution image of the Jupiter on the left. Then you have the 400 rank approximation SVD in the middle, and you will have the randomized SVD image on the right hand side. What you will see is you will have the original image, then you will see 400 rank approximation, and then you will have the randomized image approximation, and this will actually tell you how the singular values, how the randomized SVD is working for Q is equal to 1, Q is equal to 2, Q is equal to 3, Q is equal to 4, and Q is equal to 5. So you would notice, and I'm going to show this once again, just for my own satisfaction. So please run this code. And then you would see that initially it will display 3 images. It will display 3 images. And I'm going to show you those 3 images. And then the last image will get replaced by the plot of the SVDs. So I'm going to show you those 3 images. You should see these images, and the last image is the randomized SVD approximation of the original image. And then I just replace that with figure. So if you want to change that, you can go to share. I mean, actually the Matlab screen. And then you will see you can actually take this off. And then run. And then you should be able to see the 3 images. And this is super duper important. That now this actually just shows you how the SVD is decreasing. Okay, any questions? Now, what I want you to do is, I didn't show you here, but you can add TikTok and just try to find out the amount of time that takes to perform the randomized SVD and the regular SVD. And if you think the other thing to do is, actually, this is something that you can play with, that I'm reading an image of Jupiter, JPEG. This is actually not a big image. So if you were to look at this image, it's not a very large image. So if you have a super fast computer, yeah, you can actually perform this calculation very easily. I would encourage you to try this on a very, very big image. The last part which I want to talk about is something called as the tensor application. And please open the code C tensor. So this code is talking about the tensor decomposition or the factor analysis that we talked about. Now, what I want you to do is, so what is happening in this example? So in this example, we are, again, it's a sort of a toy problem, and we are trying to construct a 2-factor approximation. It's a toy problem, and we are going to construct a 2-factor composition. So what I want you to do is, you can run this code. And then you will see that you can construct a tensor. And that data matrix is basically 121 by 101 by 135. So what I want you to do is run this code. Then you're going to see those data sets that are constructed. So when you construct the data set, this is the data set that you are going to get. This data matrix is basically a tensor. It's a 3-dimensional matrix, which has 121 multiplied by 101 multiplied by 315. And what we want to do is, we are going to use something called as the CT, tensor decomposition. We are going to use something called as the CP, tensor decomposition, to extract the underlying structure of this data set. So we are going to use and then I would encourage you to try this code, play with this, and then you'll see that you can actually perform the decomposition in 3 dimensions. So basically, you can actually have a nice spatiotemporal function. This is the spatiotemporal function. As you can see, it is varying in time, it's varying in X, it's varying in Y, so it's actually a tensor. And then what you are doing is you can actually perform the analysis and then actually decompose this into its fundamental components. So I'm going to stop here today, and I just have to caution you that the material that I presented today, especially the Matlab code, it's not straightforward. So I would encourage you to go line by line through the codes that I discussed today. Because if you're going to work on the project for the linear algebra, I would suspect that you will have to use some of these codes, or you have to rework or change these codes so that you can utilize these codes properly. So I'm going to stop here, and I'm going to let you ask if you have any questions. I would be happy to answer any questions. Any questions on the code? Everybody got the codes working? So the important examples today we looked at Eigenfaces. I would encourage you to just Google Eigenfaces example. This is a very famous example. Then application of Eigenfaces. Then the SVD. RSVD is super important because that is what is used in PageRank and all those Facebook and all other applications. Yeah, I wouldn't worry about that parafact code at this point. You should be able to do the CP tensor without any problem. Yeah, you have to go through line by line, and this is a perfect time that I would encourage you to look at the book, the textbook, the linear algebra and learning from data. There, the author talks about the CP decomposition, tensor decomposition, and all that. He also talks about the randomized linear algebra and randomized SVD, but this is how the randomized SVD is used. And then this is how randomized SVD is applied. Okay, so if there are any questions, I would be happy to answer, or I'm going to have my office hours today. Can you? Yes, PCA is sort of feature extraction and sort of pattern recognition or pattern classification. It's used, that is what the PCA is all about. So PCA can be thought as unsupervised machine learning. So PCA is unsupervised machine learning. Yes, PCA captures the variance. If you look at the theory of PCA, PCA can be studied from linear algebra point of view, or principal component analysis can be studied from statistics point of view. If you study PCA from statistics point of view, they would actually say it in terms of variance. But if you look at the PCA from linear algebra point of view, it's nothing but mean subtracted SVD. So I would just use SVD. I would just use mean subtracted SVD. And if you want to see the code for Eigenfaces, so this is where we are actually subtracting the mean. Not here, here. Yeah. So basically here. So this is where we are doing the PCA. So here, actually the PCA is captured. This is the mean subtracted SVD, and that is nothing but PCA. So line number 11 is where we are performing PCA. Yes. Oh, principal ICA, there is a difference between PCA and ICA. ICA stands for independent component analysis and PCA stands for principal component analysis. Again, those are baseline features, but mathematically, it's different. And we are going to cover ICA, a little bit of ICA in next few lectures. So at that time, I would explain to you how ICA can be. So in certain applications, PCA is better, and in certain applications, independent component analysis is better. But I will explain that. Not today, maybe after a couple of lessons, but we are going to talk about it. So if you can wait for a couple of lessons, we will talk about it in depth. Yes. So between analysis method, which is the best for robot vision and tagging tracking. So if you look at the modern tracking or image recognition validation techniques, they actually use multiple algorithms. So basically, it's not just PCA. PCA combined with some additional stuff that is used for tagging and tracking. But fundamentally, if you want to start doing some image processing, image tracking, you will use these PCA SVD techniques for the baseline data analysis, and then you will build on top of it. So again, I'm not an expert in machine vision, but if you go to a machine vision class, they will start with PCA, ICA, or if you go to perception class, you will again see PCA, ICA, all that stuff, or SVD. Okay, I'm going to stop recording and I'm going to stop share.